Many of the functions you see are not the nice parent functions, but transformations of them. Now, many functions are not going to be transformations of parent functions. They actually cannot be written in that form. But you can see transformations of both parent functions and other kinds of functions. And function transformation is always written like this, where you have some function f of x, and then you have these four real numbers that are specified, a, b, c, and d. Now, if a and b are just 1, and c and d are 0, you get the function back. So a and b equal to 1, c and d equal to 0. These are like the baseline things that no transformations has been done. But anything changed from these baseline measurements will transform the function. It's important to note, just like in order of operations, multiplication transformations, so a and b, will happen first, and then you're going to do what c and d do to it. So I've got a little graph set up here. This is the actual function itself. It's this long function here. That's not really that important. What is important though is that I have the actual transformation, a times f of x and all that stuff, and then I have sliders for each one of these things. And we're going to look to see what does each one of these things do to the function itself. And we're going to answer these questions down here about each of the parts. So first off, let's look at a and b. If we increase a, so a at 1, right? This is the baseline measurement. This is no transformation. If I increase a, look at the graph. The blue is going to be the function that's been transformed. The red is the original function. So I'm increasing a here, and you can see the function is being stretched more and more vertically. And if I go between 0 and 1, so if I go from 1 again, I'm going to go down from here, down to 0. You can see it's getting more and more flattened. And it actually gets more flattened all the way until I hit a equal to 0, which I can get it here. Oh, a little bit. Let me just type it in. A equal to 0, you can see it's been completely flattened out to the x-axis. So back from 1, if I instead plug in -1, well, here we have a vertical flip. This point here from the original red function got flipped across the x-axis to this point. This valley got flipped to be a peak. The peak goes flipped to a valley, valley to a peak, and so on. They just get flipped across the x-axis there. And then if I go large A, for instance, a to -10, you can see it's been stretched. So it's been flipped and then stretched. And finally, if I go less than, or I should say greater than -1, but less than 0, so for instance, 0.5, -0.5, it's not looking as clear. Let me go a little bit smaller, go 3, 2, 1. You can see it's being flattened. So it's been flipped and then flattened down. And that's what we're looking at here. If it's greater than 1 or less than -1, it's going to be stretched horizontally. If it's between -1 and 0, and then 0 and 1, it's going to be compressed vertically. This is all in the vertical direction. And of course, the negative will flip it vertically. So that's what we're looking at here. This is going to be a vertical stretch. And between 0 and 1 is a vertical compress. A compression of some kind. -A will flip vertically. And then of course you do a stretch or compression if it's less than -1 or between -1 and 0. Okay, now B is also a multiplier. Okay, so back at A equal to 1, check out B here. So if I increase B from 1, the baseline measurement, I'm just going to increase it a little bit. You can see, oh, it's getting flattened and flattened and flattened horizontally. Then if I go between 0 and 1, you can see, well, this is going to start getting stretched out horizontally until I hit 0, and it gets completely unraveled, completely stretched out. And actually, it ends up being stretched out across the y-intercept there. That's just because it's being stretched horizontally. Now, if I go to negative b, between negative, let's go to -1, that's a flip horizontally, right? This point came from this one in the original function. The original function here gets flipped over to this side. It gets flipped across the y-axis. If I go up from -1, between -1 and 0, it's going to get stretched horizontally. And then from -1 upward, it's going to get compressed horizontally. That's interesting because, right, when we increase from 1, it gets compressed horizontally. But when we increase from 1 from A, it gets stretched vertically. So there's actually this difference between B and A, where it does kind of the opposite behavior. It stretches versus compresses in its respective direction, depending on if it's greater than 1 or if it's A or B. So yeah, so B greater than 1, this is going to be a horizontal compress. Between 0 and 1, it's going to be a horizontal stretch. And of course, negative B is a flip horizontally. And of course, as I said before, when A equals 0 or B equals 0, really x disappears in the constant or in the function. So if A is 0, this whole portion here just goes away. And then you just get D. So you can have some y equal to D. If D is 0, it would be the y equal to 0, the x-axis, or some number. And then if B is 0, then really all we have is negative C is getting plugged into the function. And then whatever that gives you, that's just going to give you a number. A times whatever that is plus D, that's just another number. And you'll get, again, a horizontal line. So with either of those being 0, you're really just going to get a horizontal line. No interesting behavior from that. Okay, now C, A and B were the multipliers, so those stretched and compressed the function down. C and D work a little bit differently, and C especially so. It works even more differently than D because there's this interaction between C and B that you have to always keep in mind. And that is, let's go back to the standard baseline of 1 for A and 1 for B. And now what we're going to do is we're going to change C. So I'm going to increase C. You can see that the function is just being shifted to the right. When C is 10, the function gets shifted to the right. It's important to note that what this will look like is it'll actually look like it's negative in the actual function transformation. But it's not, because it's written as bx minus C. So you might see, like, for instance, f of x minus 4. That's actually a shift right of 4 units in the positive x direction, even though you might expect it to be shifting left 4 units. Well, if C is negative here, then you see it's going to get shifted right. Now, that only happens because, let me put it back at 0, that only happens because B is positive. If B is negative, for instance, I'm just going to make it negative, something bigger like that. If I increase this now, you can see that it's being shifted to the left. And then if I make it negative, it gets shifted to the right. And the interaction really depends upon this fraction here, C over B. If you take C divided by B and it's greater than 0, then you have a shift leftward. No, sorry, a shift rightward. If it's positive, you'll move it to the right. If it's negative, however, it's going to be a shift leftward. So that's important to note. B here was negative. If C is positive, C divided by B will be negative, and you can see it goes in the negative direction. If I change it to be negative, then C divided by B is a positive number, And you can see it's being shifted more and more to the right. Of course, if B is positive, C positive makes it go right because positive divided by positive isn't positive. And if C is negative, negative divided by positive is negative. That's going to shift it to the negative direction. Just remember, it's going to always look opposite when it's inside this thing here, unless B is negative or positive. So you just have to keep that in mind. It's a tricky thing to have to deal with when B is something different than 1. Okay, finally we have D. D is the last one. D and A are really the simplest. When D is positive, it goes upward. When D is negative, it goes downward. A doesn't really change that. D positive goes upward. D negative goes downward. So A and D are kind of the nicest ones to work with. So D just shifts up and down. Okay, so A and B multiply, so they either stretch or compress. And negative A or B flip. Now C and D add, so they shift. Left, right, up, or down, whichever direction it is. Now, inside the function, we have B and C. And B and C worked in the horizontal direction. A and B are on the outside, and they work in the vertical direction. Those are the key things to note if you can't remember what each one individually does. Of course, you can just graph the functions themselves and play around, right? A is in the vertical, D is in the vertical, B is in the horizontal, C is in the horizontal. Okay, really there's no reason to ever do this stuff without graphing software. If for some reason you have to, then you can use these techniques to help you out. But always use graphing software to clarify. These things are very easy to make mistakes on. I make them a lot because it can be hard to remember each and every single little detail. That's why you should always graph. Use some software to help you out. For this example problem, I have this function here. I've just dotted it so you can know or see which one was the original function. This is f of x. It's actually a solid line, but once again, I just dotted it so you can see it exactly. But this is f of x. And what we're going to do is we're going to take a look at these 3 transformations and ask, what does the function look like after we transform it? Well, always keep in mind the multiplication transforms first. So in this case, we have 2 transformations, right? This was what it looked like. A times f bx minus c plus t, right? That's what the function transformation is. So in this case, a is 1. That means no transformation with a. B is 1/3. So if b is between 0 and 1, that's a horizontal stretch. And it's not going to be a stretch by 1/3 because that would actually be a compression. It's in fact going to be a stretch by 3, by the reciprocal of this. So we're going to stretch it out by 3 units, or I should say we're going to stretch it by a factor of 3 units. And then we're going to shift it downward. Since d is -2, we're going to shift it downward by 2 units. So horizontal stretch by a factor of 3. This is -2 for the x coordinate. That's going to be stretched over to -6. This coordinate up here is at -1. That's going to get stretched over to -3. This spot here is on the axis, and therefore it will not get stretched anywhere else. It's going to stay there because it can't get stretched anywhere. It's right there on the zeros. So think of it like 0 times 3 is still 0. This point's going to get stretched over here to 3, and this one here to 6. So with that in mind, we can plot these points. this is going to look like this. Something to that effect. Not completely accurate, but it does the job for our purposes. That's the stretch. Now we have to shift it down 2 units. So everything here just gets shifted down 2 units. So it's going to look something like this. This point's the main one to keep in line. There we go. Okay, so that's our first function, which is y1. Okay, the next one, we have c equal to not -4, right? It's minus c. So c equals 4 here. And d equals +3. Since b is not involved at all, right, we have b would be just 1 here, and so is a. C over b is 4 over 1, so that's going to be 4. That means it's going to be shifted right 4 units, and then up 3 units from d. So the same shape, I'm going to look at this central point here, shifted right 4 units, so we have 1, 2, 3, 4, up 3, 1, 2, 3. And then it's going to have the basic shape, the same basic shape as it had. Something like that. So this is y2. Okay, finally, we have a equals -2. So we know it's going to be a flip vertically and a stretch vertically by a factor of 2. C is -3. B is 1, so we know C over B, -3 over 1, just going to be -3. It's going to be shifted left 3 units. And then D is +5, so shift left 3 units and then up 5 units. Okay, let's do the multiplication transform first. We're going to flip it first, so keep deleting that F. We're going to flip it first, so this point here goes down to right here. And then it gets stretched by a factor of 2. So this is at -1, multiplied by 2, it's going to go here. This point's going to get flipped down to here. It's at -2 times 2, goes up to 4. Sorry, -4. This point goes here. This point stays the same because if it's getting stretched, flipped on 0, 0 times -1 is still 0, then 0 times 2 is still 0. So this point will not get moved anywhere yet. And this point here, this point's going to get flipped down and then stretched out to there. So it's going to look something like this from just the vertical transform. We haven't done any shifting yet. So kind of a picture in your mind. Do you see how that's a flip and then a stretch by a factor of 2? And then from here, we're going to shift left 3 units. So I'm going to take this central point, left 3 units, 1, 2, 3, right here. And then shift up 5. 1, 2, 3, 4, 5. That's the central point here. So we're going to go down 2 over 1, down 2 over 1, over 2, over 2, over 1, up 4, up 2. All right, and that's going to give us our final answer here. I can draw accurately somewhat. There is y3. Okay, so for this one, we looked at a function and then the transformations in the algebra and then showed it geometrically, or showed it on the graph. For this next one, let's look at the graph and then look at what are the transformations that we can write using the algebra. And just so you know, this function is actually the square root of 2. Sorry, the square root of x, not 2. And I've just capped it at x past 4. So you can always test these yourself, test the transformations yourself by graphing it, seeing if it does look at the same. Of course, it's just going to keep going on indefinitely this way. Like all these are going to go on indefinitely. But I didn't want to have to draw the whole thing. That's why I capped it. at x equal to 4. Okay, now from this spot, we're going to transform it to g of x first. And the first thing I'm going to look at are the transforms, the stretching and compressing. So to do that, I'm going to look at the distance that this thing looks at. So first off, I can see that from this point, I'm going to go up 2 units and then over 1, 2, 3, 4 units. That's the kind of overall shape that I have. Now for g of x, I'm going to go down 2 units, then 1, 2, 3, 4. It's the same distance, 2, 4, 2, 4. What that tells me is that this thing has not been stretched or compressed vertically or horizontally. I have the same thing. I do, of course, see that it's been flipped vertically. This spot has been flipped down to here. So this is the flip portion first. And then we can take this spot here and count and find what are the shifting transforms to get to this spot here. So it's been shifted over 1 unit and then up 1, 2, 3, 4, 5, 6. So we know it's been flipped vertically. That means A must be -1 because it's not been stretched vertically or compressed vertically. B hasn't been changed at all, so B must be 1. It's been shifted over by 1 unit, and since B is 1, that means C must be 1 as well, because C divided by B is 1 over 1, so 1. And then we know it's been shifted upward by 4 units, so D must be, 6 units upward, D must be 6. So if the original function is f of x, that means this one must be negative f of x. It was minus c, right? Bx minus c. And then plus d. So plus 6. As I said, f of x equals the square root of x. That means that if you want to test this out for yourself, this is what the transformation should look like. It should be that one here to get this graph right here. All right, let's look at h now. So same idea, it was 2 up, 4 over. This one is now 1 up, 1, 2, 3, 4 over. So we can see that it's been, this was 2, it's been compressed vertically by a factor of 2, right? It's been compressed down to 1/2 its size. That's the same idea as being compressed by a factor of 2. Either way you think of it, that means A must be 1/2. It's not been flipped horizontally or vertically, so A would be positive, and it has to be 1/2 the height. Since A between 0 and 1 is a compression, that's why it's 1/2. If it had been horizontally compressed by half of its length, then B would actually be 2 because B greater than 1 is a compression. Just go back and look at those transformations I did above. Now, nothing's happened horizontally, so B is again 1. And we can see here, right, it's been shifted over 1, 2 units and shifted down 1, 2, 3, 4, 5 units. Since B is 1, that means C has to be -2, right? C over B is going to be this shift here. B is just 1, so C has to be -2 to get that shift of left 2 units. And then D must be -5. All right, the function is going to be just positive 1/2 f x plus 2, right? It's always x minus c, so here we have -2, and then -5. And test that for yourself. Try graphing that and seeing that it's actually true. Okay, give these ideas a try in number 1. And try it out in number 2.